Okay, now that we finished Section 11.1, we're going to go on to the derivatives of exponential functions. These are actually much more common, and especially in the fields of physics and in the fields of rates of change. Rates of change when we talk about finance, we talk about mortgages, we talk about investments. In physics, we talk about half-life of radioactive elements. Everything sort of has an exponent. So this is it's a little bit more important, especially for business applications. The basic exponential function is y equals ae to the bx. B is your base, a is a constant in front of it. Now when you took exponents, I talked about the sensitivity of b and the sensitivity of a. I'm not going to do that now. I'm going to assume a is 1 and b is 1, make it a little bit easier. And I'm going to plot y equals e to the x versus x. Notice when x is 0, e to the 0 is 1. Anything to the 0 is 1. The y-intercept is 0, and the exponential keeps going up and up. It's called a positive exponential. If I had a negative in here, it's going to go in a different direction. It's going to go down, just like slope of a straight line. This positive goes up, negative down.
The y-intercept is 1.
The y-intercept is 1 because when x is 0, y equals 1. E to the 0 is 1. Now, the derivative of it would be the tangent line. The tangent line would be the slope of the tangent line to any point. Here I have a tangent line to the point 1. So the slope of that tangent line to point 1 would be the derivative. But what I want to do is something I don't really usually do in this class, is derive the derivative because it's so counterintuitive. And here we have 3 log rules. Remember log rules again? The log of a product, there's your base, the same base that's there, of x times y is the log of x plus the log. So product is additive, which we know. The log of a division problem, quotient, is subtracted. And this is the one we're really interested in right now, is the log of something raised to a power. Notice, as was pointed out to me, the base is a little b and the power is a big A, because you want to know it's the power that gets brought down on the same line as the log of x, allowing you to solve for that A. You cannot solve it when it's in the power. So let's derive the law of basic exponential derivative rule. Okay, let's just take the natural log of e to the x. Let's apply the log rule here. Now this could be natural log. What is the natural log? Well, natural log is the log to the base e, okay, of x. That's what ln is. So I can use this rule. It says take the exponent and multiply it times the log. Now you're going to know that the natural log of e is going to be 1. So if you put it in your calculator, you'll find the natural log of e is 1. So this gives me the natural log of e to the x, gives me x times 1, which is x. Now, I'm going to take the derivative of both sides. Okay, well, let me do that on another line because it gets kind of confusing. Okay, I've been doing it in steps so far. Why change it? Well, what's the derivative of x? The derivative of x is simply the number in front of it. So this is equal to 1. What's the derivative of the log of e of x? Okay, well, remember our log rule? The derivative of the log of u is 1 over u du dx. So let me erase the top now and finish this. we have our exponential functions that they all look about the same. Depends on whether you have a positive or a negative slope. There was a voice from nowhere. Okay, I'm in a house with a whole bunch of people. You may hear weird voices. Just ignore them. Okay. So what we're going to do now is we're going to let u equal the natural log of, actually no, I'm going to let u equal e to the x. It's the argument here. Okay? So du dx actually is e to the x. So I really don't solve too much by doing this, but we'll show you what happens. In fact, I'm not going to do that. Here's what I'm going to do. Let me revise what I have here. So I'm going to revise what's in your notes. Okay, so if u is e to the x, therefore the derivative of my log of u is going to be 1 over e to the x. And I'm going to say d dx e to the x because I'm going to pretend that I don't know what this is. So du dx is d dx e to the x. And I'm going to pretend that I don't know what that is. And I know that this is 1 on this side. Okay? Now, let me take e to the x and multiply it by both sides. I'm going to multiply e to the x by both sides. Crosses that out. And I get the derivative of e to the x equals e to the x. That's your rule. See, I pretended I didn't know it, so I just put it back in the equation as is. And that gives me your rule. Counterintuitive, but the derivative of e to the x is simply e to the x. So put that somewhere in your brain because we are going to use it. And I'm looking for my eraser here. So let's do a few. This is a very simple rule. Now I'm going to give you a log rule, but this is basic. All the rules are based on this. So for example, let's take the real rule. The rule, let's say this is it. The derivative dy dx, write that down, sorry, given y equals e to the u, okay, where u is any function of x, or it could be a constant, or u could be a constant too. Well, then that's 0, right? All right, so then dy dx is going to equal to e to the u du dx. And this is your formula for any u that could be in the exponent or the power. Now notice here u is x. So if we would do this one here, and we had y equals e to the x, we would say u is x and dy dx equals 1. So using the rule, we would have dy dx equals 1 over u, 1 over x times 1, or simply 1 over x. But that's not right, is it? Because that's not the rule. Okay, that's the rule for logs. So let's use this rule here. How many times when I see people do something, well, when we're going from logs to exponents, they simply put 1 over x again? No, this is your rule. Make sure you understand these rules. I will put these rules on a sheet. But if you're going to use the rules for exponent, make sure there's an exponent in the rule. Okay, so this is going to be what? This is going to be e to the x times 1. So it's e to the x. So once again, that simple one over here pops up again. Now let's get to more difficult problems. So we've actually, okay. Let's get, I have time for one problem. So let's take, by the way, when you're transitioning from logs to this, make sure you actually differentiate the logs from exponent. One of the most common problems I see is people take exponent and use the log rule. People take logs and try to use the exponent rule. Okay, so let's take an example. And we're going to say y equals e to the 4x third. Y equals 4 e to the 5x third. Find dy dx. Well, we're going to let u equal the exponent. We're going to let du dx equal 15x squared. Okay, now dy dx is going to be what? Well, guess what's missing from this definition that's in the book? Guess what's missing? They don't have, this assumes a coefficient of 1. So if we go back here, what we have to do is change this to a, and that means when I do this, the coefficient will be multiplied by that. Now the book doesn't do that, okay? That's an added thing that I added on. As you can see, this is why I did this problem. There's a 15 in there. So you have to define a then. So now instead of defining u dx, a, so dy dx is going to be a e to the u du dx. That's going to be 4 e to the u, which is e to the 15x squared, 5x third, times 15x squared. 4 times 15 is 60, x squared, e to the 5x third. And that's your solution. Don't forget to change that. The book does not put an a in front of there. Okay? Very important. A lot of calculus books assume you're going to know that the constant does that. But they assume that a equals 1. But a is not all equal 1. As you see, it's equal to 4. So this is your better rule. Okay? So we're going to do another one. I don't know if I have time before. All right, so when we come back, we will do some more examples of the exponential rule. I'll put the exponential rule in a corner, and we can use it all the time. All right, see you when we get back.